Hello class, welcome to today's lesson, which is lesson 5 of topic 5, increasing and decreasing functions. And these are the definitions of an increasing function and a decreasing function. Let me highlight those two words, increasing and decreasing, okay? But let's first talk intuitively about these two definitions. It's very simple to understand. For example, suppose that I'm going to give you a function, or more specifically the graph of a function, and let's suppose that such graph does something like this. There you go, more or less. Okay, then we can see that we can part the graph into these sections, guys. For example, I can make a partition right here, and then over here, more or less, and then um, from here to infinity. So we have like three sections basically, from minus infinity to this part, and then from this part to this part, and then from this part to plus infinity. And we can realize something right away. You know, in this part, you can actually think that this is like a roller coaster, okay? And from minus infinity to this point, which I can label, let's label it A, and this let's label B. You can see that if you were displacing from left to right in the x-axis, the function is increasing, okay? And if this was a roller coaster, you can see that basically the roller coaster is going up, okay? It's going uphill. And then from A to B, when you move from left to right in the x-axis, then the function is decreasing, okay? It's being less and less and less, or the roller coaster is going downhill, like so. And then once again, from B to plus infinity, we can see that the roller coaster is one more time going uphill, or the function is increasing. And that's all, intuitively speaking and conceptually speaking, that's all that these words mean, increasing and decreasing. We say that in the interval from minus infinity to A, the function is increasing, okay? And then from the interval from A to B, the function is decreasing. And from B to plus infinity, we have that the function is increasing one more time. And this kind of thing can change many times over. For example, I can create another function that does something like this, okay? And I can spot these three, one, two, three, four parts, okay? Let's call them A, B, C, and D. And I can see that the function is increasing from minus infinity to A. The function is increasing. And then from A to B, the function is decreasing. From B to C, the function is increasing one more time. And then finally from C to D, the function is decreasing. And now from D to plus infinity, the function is increasing one more time. So you see how it works. It's basically going uphill or going downhill when we move specifically from left to right in the x-axis. Okay, so that's all it means. And these are the formal definitions, these two definitions. Let me erase this second diagram. And let's talk about the definitions very quickly. Number one says a function f, let's suppose this is function f, is said to be increasing over the interval a comma b if for all x1 and x2 in the interval, in such interval ab, we have that if x1 is less than x2, then f of x2 is greater than f of x1. I made a mistake here. There you have it. Actually, we can put it in this way. I think this sounds much better. If x2 is greater than x1, then f of x2 is greater than f of x1. Yeah, I think that that sounds better. And what does this mean? It means the following. For example, if you choose an increasing interval from here, for example, this one, what you can find is this. If you choose any 2 points in here over this interval, and you label them x1 and x2 or whatever other thing, it doesn't matter, and then you locate their corresponding values of the function, which would be obtained in this way. This is f of x1, and if this is x2, then we trace this perpendicular to the x-axis, and then this other perpendicular to the y-axis, so that we can find f of x2. So basically what we can see is the following. If x2 is greater than x1, which in fact they are, okay, then f of x2 is greater than f of x1. You see? And that's what the definition of increasing means. That if you take two numbers in this interval, okay, two numbers like so, and if one is greater than the other, like so, then the function evaluated in the greatest number will be also greater than the function evaluated in the lesser number. That's how it works. So as long as your function satisfies this definition, we can say that it's increasing over this interval. And the same works for the other definition for decreasing. Let me one more time. Let me draw this diagram more or less. Just a diagram doesn't have to be very clear, or a sketch. That's what I mean. And one more time, for example, we know that the function is decreasing. I mean, conceptually, we know that it is decreasing from A to B. Okay, in this section, the function is going downhill. So let's see if it satisfies this definition. What does it say? A function f is said to be decreasing over the interval ab if for all x1 and x2 in such interval ab we have that if x1 is less than x2, then f of x1 is greater than f of x2. Pay a lot of attention, guys, to these two statements because they are different. Okay, just they are different only in this sign, okay, in this greater or lesser sign, but that makes the whole thing different. For example, if I choose two numbers here and I label them x1 and x2 or whatever I want, and then I locate the values of the function x1, therefore this is f of x1, this is x2, therefore this is f of x2. We can clearly see that f of x1 is greater than f of x2. Okay, so in this case we have the following. If we have the following, if x1 is less than x2, which in fact that's the case, x1 is less than x2, then f of x1 is greater than f of x2. You see, f of x1 is greater than f of x2. So this is what it means to be a decreasing function over such interval, over the interval a and a to b. If you pick any two numbers in this place in such a way that one is greater than the other, then the function evaluated in the greatest number has to be less than the function evaluated in the lesser number. You see, it's very simple to understand. The concept is more simple to understand than the definition, but once you understand the concept, the definition comes very natural. Okay, fine. Now, what else? What else can we say about these functions? How do we know, for example, if I give you a function, any function whatsoever, for example, this function, okay? How do we know over what intervals this function will be increasing and over what intervals this function will be decreasing? Well, we can help ourselves with calculus. Okay, we can know with calculus, more specifically with the derivative of this function. Let me tell you why. This is another application of the derivative. Knowing in what intervals any function whatsoever, any function will be increasing or decreasing. And let me explain to you why. First, conceptually, one more time, just conceptually. For example, if we have this function f, you can agree that the function is increasing over this interval from infinity to a, and then it's decreasing from a to b, and then it's again increasing. Now, remember that the derivative helps us find one thing, and that one thing is, at this point, finding the slope of the tangent uh, to the graph of this function at any point I want. And you have to understand this, guys. When, for example, if you go over deciding these 3 points, for example, one point over the increasing period, over the increasing interval, another point over the decreasing interval, and another point over, one more time, the increasing interval. If you calculate the slope, basically if you draw the slope to the tangent to the graph of f at this point, you will see that the tangent has a positive slope. Remember that lines that look like so, like this, all of these have positive slopes, and lines that look in these directions, okay, tilted in this direction, have negative slopes. I hope you remember this. And I'm taking into reference, of course, the normal Cartesian plane, like in this direction. Okay, all the lines that look like this with these inclinations in this direction, all of these have positive slopes, and all of these have negative slopes. Okay, so basically what I was telling you is this: in any point which is on an increasing interval, when you graph the tangent, okay, to the graph at that precise point, you will see that it has a positive slope. And what happens when you draw the tangent, I'm sorry, to the graph of the function at a point which belongs in a decreasing interval? Well, let's see. It's right here. And as you can see, the tangent has a negative slope, you see? And one more time, this other point belongs in an increasing interval, and the slope is one more time positive, the slope of the tangent. And that happens all the time, guys, okay? The slopes, let me write that down. The slopes of the tangents to f over increasing intervals are positive, and over decreasing intervals are negative. So we know about that. Okay, and these other things, guys, in here, look, I'm gonna erase these 3 tangents. Oops. This, and we should be aware of these other things, okay? These summits and these valleys, okay? This one right here, this point, and this other point. We can call this a valley, and this an apex or a summit, something like that. This is not the precise name. You're gonna get to know the precise name a little later. And you can see that that basically the function changes behavior once it goes past these 2 points. Okay, after this point, I'm sorry, before this point, the function was increasing, and after this point, the function was decreasing, 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 and then after this point, it goes up again, increasing. So these are like inflection points. Okay, And in fact, those are the proper names. Inflection points, because that's inflection points, because that's where the function changes behavior. Okay, so basically, at what happens at those 2 points with regards to the tangent? If we draw the tangent at those points, okay, what can you observe? What is the slope of these two tangents, guys? What is the slope of a horizontal line? The slope of these things is 0, right? In both of them. So basically, we can see that the changes in the direction of the function, whether from increasing to decreasing or from decreasing to increasing, happen always at these inflection points, which always have slopes of 0 to their tangents. Okay, so let's see how can we solve this problem. Okay, the problem is, given this function, how can you know in what intervals this function will be increasing and in what intervals that function will be decreasing? Well, what you have to do is this. I'm gonna do it over here. I think with just one example you will be able to understand what's happening. So first thing we have to do is differentiate such function. You can do that already very quickly. That's going to be 6x squared minus 4x plus 3. So this is the function that when differentiated, you get this. Okay, this is the derivative of this function. And remember, the derivative tells you the slope of the tangent in the point x. Okay, so basically, if you want to know, for example, the slope of the tangent at point, I don't know, 2 comma 1, 2 comma 1, then all you have to do is evaluate f prime of 2 and you get the slope of that precise point, the slope of the tangent. Okay, now what I can do next is this. I can ask myself for what points x is f prime 0. Okay, so basically for what points of this graph of this function I get that the slopes of the tangents are 0. Okay, so basically what I do is this. I'm gonna write my derivative and I'm gonna evaluate it to 0. Okay, I'm gonna say, okay, for what points, for what values of x will this be equal to 0? Then I'm gonna solve this equation. Does this have a quick factorization? Let's see. 3x, 2x, 1 and 2. No, it doesn't. Okay, so we have to help ourselves with the general formula. So basically, x will be equal to 4 plus minus 16 minus 4, 3 times 6, and this won't have no, this 16 times 4, 3 is 18. No, this won't have any real solution.